Hi, I'm Whitney Espick, the CEO of the MIT Alumni Association, and I hope you enjoy this digital production created for alumni and friends like you.
Hello and welcome, MIT and Caltech alums and friends, to the MIT Forum for Equity. I'm Joe McGonigal, Alumni Education Director at MIT, and along with George Coe, Director of Alumni Strategic Partnerships at Caltech, we'll serve as your hosts today. Today's broadcast is sponsored in part by the MIT Federal Credit Union, MIT Professional Education, and the MIT Mind, Hand, Heart Community Innovation Fund. We especially welcome Caltech alumni to this forum, and we're grateful to the Caltech Alumni Association for their help in producing today's special event. We welcome your questions and input during this discussion. A reminder that conversations on equity issues are often difficult, and we all benefit from active listening, respectful communication. For those joining us on Zoom, please use the Q&A feature found on your toolbar and use the chat for any other discussion. We'll get to as many questions as we can in our 90-minute session today. We're here to discuss the challenges facing fields of science in terms of equity and inclusion today, and in particular, math and physics. Joining us are two alums of our institutions, one from MIT and one from Caltech. Jim Gates, MIT class of 73, PhD class of 77, is a theoretical physicist. He's currently the Brown Theoretical Physics Center Director, Ford Foundation Professor of Physics, Affiliate Mathematics Professor, and a Watson Institute for International Studies and Public Affairs Faculty Fellow at Brown University. Edray Goins is Caltech class of 1994, Professor of Mathematics at Pomona College. Both gentlemen are leaders in their fields. Gates is president of the American Physical Society, and Goins just finished a 5-year term as president of the National Association of Mathematicians. So they're well positioned to reflect on the work ahead for their respective fields in terms of equity in hiring, retention, and cultivation of new talents in the field. We hope they'll also share with you, of course, some current research. We'll post a link to their full bios in the chat. First, we've asked each to give us a glimpse into that research and a few opening thoughts on the state of their professions today in terms of traditionally underrepresented populations. And we'll start with Edray Goins from Caltech. Welcome, Professor Goins.
Yeah, thank you very much for that introduction. Let me go ahead and share my screen here. So what I'd like to do is actually have this presentation in two parts. First, I'll spend some time just saying a little bit about the research that I work on. And then second, I do want to spend some time giving a big overview of mathematics. I am in the Department of Mathematics. I've been very involved with different professional societies in mathematics. So I do want to say, what's the big picture in terms of what's been happening with diversity? But I think because we have this meme on the internet now of how it started, how it's going, I figured I should start with that. As was said, I started at Caltech in 1990, finished in 1994. This is actually a picture of me during my freshman year when we established the Caltech chapter of what essentially was the Black Student Union. We actually call it a local chapter of the National Society of Black Engineers. That year, I was also involved with a Ditch Day stack, as freshmen are known to do. So you can actually see an early picture of when I was just 18 years old during my freshman year. Nowadays, of course, I'm looking a lot older. So here's a picture of me teaching linear algebra at Pomona College, which is about an hour or so going east of Caltech in Pasadena. And then here's a picture of me actually at Caltech's campus just 2 years ago. When I was an undergraduate, I focused quite a bit on the history of the Black students at Caltech. And nowadays, Caltech has been really gracious to feature some of the work that I did, but also to have various displays around campus on this history of Caltech's Black students. So here I am actually with Bill Hutchinson, who also is a Black alum. He graduated back in the 50s, I believe it was. And we're here at Caltech's campus in front of the display. So what kind of math problems do I personally work on? I figured that since we have a wide-ranging audience of probably physicists and mathematicians, let me start with a question that I think perhaps everyone at least will appreciate. Let's start with a right triangle that has rational sides. I'd like to know what rational numbers n are the areas of such triangles. So for example, I might have a 3, 4, 5 triangle, right? This is what's coming from the Pythagorean theorem. And because I have a 3, 4, 5 triangle, this means that the base has length 3, the height has length 4. So if I compute the area, 1/2 base times height, then I expect to find the number 6. So what I want to know more generally is, what are other numbers that have such areas? So it turns out that you can actually relate this question into one involving what are called elliptic curves. So for example, if I'd like to know what are such triangles that work, those correspond to rational numbers x and y satisfying a certain degree 3 equation, namely y squared is equal to x cubed minus n squared x. N remembers the number that I'm trying to ask this question about. You can see some of the formulas here on the screen just to give you a flavor of how this works. So as an example, I would say that, like I said before, a 3, 4, 5 triangle corresponds to area 6, but it turns out using the formulas that you see here, that that also corresponds to a rational point 12, 36 that's on this curve here. So really more generally, I'm actually interested in this curve involving x and y. We say that an elliptic curve is a curve of the form y squared equals x cubed plus ax plus b, where a and b are numbers such that 4a cubed plus 27b squared does not equal to 0. I personally am interested in the collection of complex points, x and y are complex numbers, satisfying this relation. But let me just say that more generally, people study elliptic curves for lots and lots of reasons. For example, I am classically trained in number theory, and number theorists like to ask questions about what are called congruent numbers. A congruent number is like the example that I just mentioned a moment ago. More generally, this fits into Diophantine equations, and many of you have probably heard of Fermat's last theorem, which was actually proved by Andrew Wiles back in 1994 using properties of elliptic curves. In computer science, they also are used in cryptography, so things like public key systems, or say even just making sure that your banking information is secure. And they're used in the factorizations of numbers, so either trying to determine when a number is prime or trying to take a really large number and factor into a product of primes. They're even studied in physics. For example, they're studied in questions involving supersymmetry and also questions involving string theory. And I'm going to come back and talk a little bit more about the physics aspect today. If you wanted to see more about this, I actually wrote an article in the Notices of the American Mathematical Society about 2 years ago called the Ubiquity of Elliptic Curves that goes over a little bit more of how elliptic curves are used in lots of different areas of science. But today, I want to say that my goal of studying these elliptic curves is to draw pictures. I know that may seem a little bit weird, but that's really one of the reasons I got interested in elliptic curves. So here's some examples of pictures. These are actually what are called graphs, not graphs as in y equals f of x, but graphs as in you have what are called nodes and you have what are called edges. You can see here, I've showed 6 examples of what are called graphs. The ones at the bottom, the lower 3 are a little bit different from the top 3 because I've drawn them where the edges seem to intersect. Well, what I'd like to do is draw these pictures so that the edges do not intersect. So here's a slightly different way of drawing those 6 pictures. The 3 at the top are more or less the same, but now I've wrapped them around so that they're on the surface of a sphere. Think of it as maybe I have a sheet of paper and I can stretch it out as far as I want, but then I kind of wrap up the edges to the very top so that I have one of these 3 yellow spheres you see. The 3 at the bottom are actually what are called toroidal graphs because I've drawn the graphs on the surface of a torus. Those pictures that I had before were problematic because the edges overlapped. Now I can move things around so that the edges don't overlap. In general, I'd like to draw these graphs on exotic surfaces. The fancy language is Riemann surfaces, but you can see some examples of the surfaces that I'd like to use. In general, there's something called a descendant form. This is just a fancy phrase for child's drawing. There's a way you can draw these by using what are called belly pairs, and a slightly complicated mathematical procedure that I won't worry about going over, but I'll say that really my research corresponds trying to understand belly pairs and trying to understand how to draw these so-called descent d'enfants. So here are some examples of descent d'enfants, literally just drawings that we have. These are examples of drawings on the surface of a sphere. You can see that they can start to be very simple, but they can get to be very complicated very fast. It's not exactly clear how to find some of the functions that allow us to draw these, how to find these belly maps. But this is one of the reasons I'm interested in this, how to actually find some of these maps. Those are more or less the simple kind of drawings, but you can get a little bit more interesting when you go to elliptic curves. It turns out there's a classical theorem that says that the set of complex points on an elliptic curve form a torus. There's a complex mathematical procedure that allows you to do this by using elliptic integrals and elliptic logarithms. I just wanted to give you a flavor of how complicated this could be by showing you some formulas here on the screen. But the idea is that the set of points on an elliptic curve can be wrapped around in such a way that they do form points on a torus. Now, I want to show you how we might possibly do this. So remember I mentioned that I'd like to draw these descent d'enfants. And I want to do this by using what are called belly maps. Here on the screen, I'm showing you some toroidal belly maps, some belly maps associated to elliptic curves that can get to be pretty complicated. Here on the left, you can see I have a tower of these various curves. And in the middle of the screen, you have the explicit polynomials that allow you to do this. Now, if you don't really feel comfortable with the polynomials, I can totally relate because these are some pretty nasty formulas. So let me kind of show you a graphical interpretation of what's happening. Let me take all that away and just focus on just this tower of objects on the left. I want to start at the bottom to say that I have here a line segment from 0 to 1. I can wrap that around on the surface of the sphere if I really wanted to. Now what I'd like to do is play around with this graph and lift this slightly so that I have a weird looking graph here. Think of this as maybe like an orange. And what I've done is I've kind of peeled things out so that I have now the surface of the orange in these 4 separate peels. Well, I can also think of this as the picture, the blue picture that you see here in the middle. I can go from the picture on the second line to the one at the bottom by somehow collapsing things together. But now let's go even further, move up a little bit higher. Now the picture becomes a little bit more interesting because it looks like I'm looking at lines on the surface of a torus. And then here's perhaps the most interesting one, where I've actually combined all the lines together in really weird ways. All of these that you see here on the screen are what are called descent d'enfants. And the maps that are on the left that kind of allow me to go from the top down, collapsing the lines in various ways, those are what are called belly maps. It turns out that these two, toroidal belly maps and toroidal graphs, are actually kind of interesting. They're related to what are called adinkras. And I know that Professor Gates is going to go over these in just a moment, but here I wanted to point out that all of these fancy things that we're doing in terms of writing these belly maps and drawing these descent d'enfants actually are related to a physical interpretation in string theory. And in this case, I can actually draw all of these descends as what are called adinkras. So this is actually what got me very interested in the subject, was seeing that there are these relationships between these really nice, simple equations that we might have to these really complicated looking types of graphs. So essentially, my goal in my research from here on out is to understand more about belly maps and then their connections to physics. Now here's where I'd like to shift over to the second part. And if the moderators can please just make sure that I have enough time here. I just want to spend maybe another 5-10 minutes, and I want to quickly go over this idea. What's the state of diversity in mathematics? So I'm going to say a little bit about what's happening in the organization to help frame the conversation we're going to have today. Well, there is what's called the Survey of Earned Doctorates that describes how many PhDs are given out every year in mathematics and statistics. Here you'll see on your screen from that website just some numbers that kind of say what's been happening the last 5 years. Roughly these days, there's about 1,000 PhDs that are given out in mathematics and statistics. About 1/4 of those, 238, are given out to women, and even fewer are given out to underrepresented minorities. For example, it says here, at least on this chart, that only 14 out of 1,000 PhDs were given out to African Americans in mathematics and statistics. So I want you to remember that the numbers are dismally, dismally low. Here I have a few graphs if you'd like to see some of the trends. These graphs here explain what's happening gender-wise. The blue line tells you the total number of PhDs. You can see how it kind of dipped maybe in the early 2000s in math and statistics. But in general, the number of PhDs has certainly been increasing. It's literally doubled over the last 20 years. However, the number of PhDs given out to women, this is the gray line at the bottom, has been relatively flat for the last 20 years. And this is one very disturbing trend that we know that's happening in math and statistics. On this next graph here, you can see a breakdown in terms of ethnicity and race. The yellow line at the top is actually the number of whites that have received their PhDs in math. And you can see for the blue and the gray at the bottom, those are the numbers given out to Hispanic and Black PhDs, respectively. You can see that not only are the numbers there very small, but they've also been remaining at nearly zero for the last 30 years or so. So the numbers and even the trends are really depressing in terms of diversity. Let's see, I think I'm going to skip over this here. But I'd like to say, what are some organizations that are working to increase the numbers for diversity? There's the Association for Women in Mathematics, which actually is turning 50 years old this year. So I would say that if you are interested in what's happening for increasing the number of women in mathematics, the Association of Women in Mathematics is for you. It's a wonderful organization. I am a member. I try to be as involved with the organization as I can. For those in the LGBTQ community, there's an organization called Spectra. This has been around now for, I believe, about 10, 15 years or so. But this is also a great organization that's really starting to be much more active and much more visible. There is a website called LAUSD. This stands for Latinos, Latinas, and Hispanics in the Mathematical Sciences. This website is meant to feature Latinx mathematicians by showing a profile of them once a day, pretty much every day for Hispanic Heritage Month, the end of September, the 1st of October. There's a corresponding website that actually just started about a month or so ago for Indigenous mathematicians. It's the same idea. They try to feature those that are Pacific Islanders, Native Americans in the mathematical sciences by having a profile. And again, this has only been around for about a month. And I think literally the website has only been around for a couple of weeks. So they're just now getting started. I, as mentioned, was president of the National Association of Mathematicians. This is a nationwide organization of Black mathematicians. And I was president of this for 5 years. So if you'd like to learn more about what's happening with African Americans in the mathematical sciences, I certainly highly recommend to see NAM. They've been around for 52 years now. They actually started back in 1969. And finally, I'd like to say what's happening in general, if you'd like to learn more about just women mathematicians, Black mathematicians, Latinx mathematicians, the American Mathematical Society, which is our big professional organization, has various posters that they put out featuring mathematicians from these different groups. I'd like to give a shout out to my friend John Urschel, who is currently a PhD student at MIT. You can see him here at the lower left. He's one of the few African Americans who's getting his PhD in mathematics. So I'd love to see him as an MIT alum one of these days. Now, I just want to say a little bit about what's happening very specifically with African Americans in mathematics, since this is something that is near and dear to my heart. As many of you know, I was featured in the New York Times a couple of years ago by discussing the lack of diversity in the field of mathematics. There actually were 2 articles that came out one day right after the other. The first really featured my story, but the second that I'll think I'll try to hype up a bit more, talks more about the community of Black mathematicians, how few there are at the Research One institutions. I can even say, just to call Caltech out for a moment, Caltech has only had a couple of Black postdocs over the years. It's never had a tenure track Black mathematics faculty. And I believe that it's, to this day, only had one Black PhD student to graduate. So even a place like Caltech has not done a great job when it's come to diversity. There's a great program. I'm going to actually skip over this for the sake of time. Let's move one more. There's a great program that we've actually started at a research institute in Northern California that's called Adjoint. It stands for African Diaspora Joint Mathematics Workshop. Actually, Jim Gates was involved with this during our pilot program. The goal here is to convince more African Americans to get involved in research level mathematics. We actually have quite a lot of funding nowadays from the National Science Foundation, National Security Agency, and from the Sloan Foundation. But I wanted to point out that if there are Black mathematicians out there that are looking for ways to be more involved in research, I highly recommend Adjoint. It's something that we're very proud of at the Mathematical Sciences Research Institute. And again, I do want to thank Jim here for being one of the first faculty members to be involved in running a research group. And let me maybe end with one more shameless plug. I've been involved with a project known as the Mathematicians of the African Diaspora. This was actually a series of web pages that was started by Scott Williams about 40 years ago. And the idea is that it features various Black mathematicians. It talks about their lives, about their research, about their stories. We just revamped the pages about 6 months ago, so I highly recommend that you take a look at this. This is if you're just asking very basic questions of who is a Black mathematician? How do I learn more about who's out there? So we're very proud to have this revamped work site, and I certainly want to thank Scott for working so hard in putting this site together. So with that, thank you very much for your time and attention. I just wanted to show a quick picture here of my students at Pomona College that I really am proud of.
Thank you, Professor Goins. And Professor Gates, if you would come on video and
thank you,
share with us.
Sure. Thank you very much, Joe. And first of all, I'd like to thank you and all of those responsible for putting this program together. It's a great pleasure to talk to so many people interested in the subject. I was going over the participation list and noticed a lot of familiar names. So this is a shout out to all my friends whose names I saw on the registration list. What I like to do is actually slightly different from the approach that Edray took. I was under the impression that I could spend some time digging a little bit into my research, and then that maybe in the Q&A we could talk about issues around diversity. And so my presentation is actually split up according to that. So let's get started. Let me share. Oops. Technical glitch, folks. Sorry about that. Let's try it again. Here we go. So what I want to do is actually talk about something as opposed to giving you numbers and statistics and what have you. I'm a physicist, but I'm probably the most useless kind of physicist. I often tell people I'm almost a mathematician, but to my mathematician friends, I describe myself as a fallen mathematician because I am clearly not a mathematician in my own mind. But this title has built into it something very interesting, and we're going to get back to that. So let me talk about the research that drives my passion these days. Let me first start by making some observations. These observations come from Elie Wiesel, who was a survivor from the Holocaust, and he points out to us that the opposite of love is not hate, it's indifference. The opposite of art is not ugliness, it's indifference. And the opposite of faith is not heresy, it's indifference. Now, another name that is famous among computer scientists is Alan Turing. So we've probably all heard about the Turing test. But Alan Turing had some very interesting things to say because he was a member of the LGBTQ community before it was named. And he said that made this very interesting statement that sometimes it is the people no one can imagine anything of who do the things no one can imagine. And these are the two things that I'm going to try to first illustrate in my own research. And then as we talk about issues around diversity, equity, and inclusion, I'm going to return to this. So how to get started? Well, I'm a physicist really. So I go and think about my high school introduction to science. Although I had been in love with the idea of science since 4 years old, I saw the chemical table of elements in high school. So here's a nice appearance. Well, that looked like pretty advanced in science when I was young, but however, particle physics, which is an even more advanced form of science where we look at the basis of chemistry, kind of looks like this. You can think of it as a table. In this table, I have the representation of the electron, I've got the particle of light, the photon, and then I have all the other elementary particles that have been discovered over the last several hundred years of doing scientific research. In some sense, the electron is the oldest elementary particle. A Scottish electrochemist by the name of J.G. Stoney was the first person to first imagine the electron, and he even gave it the name. Now, a lot of people think J.J. Thomson deserves this honor, but Thomson actually came after Stoney and simply verified a ratio of the charge to the mass, and thereby verifying Stoney's ideas. So if we take all these elementary particles, we can put them into a couple of buckets, 4 buckets in particular. The things like the electron go down here. We call these matter. And what this means is these are the objects in nature that forces act upon. There are the leptons, the electron, muon, the tau particle, there are associated neutrinos, and there are these small objects inside of nuclear matter that we call quarks. Now, those are the things that the forces act upon, but there's also the things that carry the forces around in the universe. And those are different objects. The particle of light actually is the carrier of the electromagnetic force. And so there are 8 carriers of something called the strong nuclear force. There are 3 different carriers of the weak nuclear force, the Z and the W. And there's something we just discovered in 2012, which is a carrier of the weak nuclear force. It's called the Higgs boson. So why do we believe this kind of stuff? Well, it turns out the thing that distinguishes physics from a faith-based activity is that we are in conversation with nature. That means experiment and observation. So one of our great heroes was Albert Einstein, and he contributed a lot. And what's really interesting is classical physics starts with Newton. Einstein was not a fan of quantum physics, but he is in fact one of the people who started the ball rolling. So what does classical and quantum physics mean to small particles? Well, I have a cartoon here to show you. This is in fact something called a Feynman diagram. I was fortunate enough to actually be in the postdoc in the group with Richard Feynman from 1980 to 1982. So I have my own Feynman stories, but that's gonna have to wait to the future. So a Feynman graph tells you how forces work. In this cartoon we're watching here, 2 electrons are those dots. That little buzzing line in the middle was a photon traveling between the 2, telling them they had to be repelled. So that's what the classical path is for particles. The quantum path, well, you know, you're always told that quantum is stochastic, it's about fractions and chaotic behavior. So I use this rather jiggly line to represent that. So what does that mean for small particles? Well, we're going to watch a quantum process here. In this example, we're going to have 2 electrons interacting by exchanging a photon, which you see in the middle, but also there'll be a second photon involved. And here we go. The electron emits the photon that it later absorbs, and in between those, they transmit a message with a second photon to be repelled. So that's a simple way to think about quantum mechanics at the level of particles. And why do we believe this kind of stuff? Well, we do observations. In fact, the most tested piece of all of science tests the idea of Feynman graphs and quantum theory. If we go back and look at those particles again, they're grouped like this. I tell people, does that picture look balanced to you? Most people would say no. Well, suppose nature actually looks like this. Now, why wouldn't we know about this? Well, it turns out in quantum mechanics, unless you have a sufficient amount of energy to observe a particle, you don't know that it's there. And so for the last decade or so, people have been looking for these extra particles called superparticles. And that's what has filled this table out and given this balance. Now, a lot of people are very discouraged because a lot of folks thought they would be easy to find. But in 2006, I wrote an article in Physics Today that said, I would not be surprised if it took us a century to find these things. And the reasons for that, I'm happy to discuss offline. But there are other reasons to believe in supersymmetry, and one of them is gravity. So let me give you some mathematical lessons real quick. That's a slinky moving along. The Higgs boson basically has an equation of motion that looks exactly like the equation for the slinky. It's just a relativistic version of the harmonic oscillator. The photon actually has a more complicated motion when it moves, and we have cartoons for that. So here we see a photon coming in from the left. It encounters a quarter wave plate, and we use a quarter wave plate to break the two parts of the photon. They're called the helicity state or the spin states. And we actually build, for example, polarized lenses to actually separate these things. Things get, it's all mathematics, folks. I tell folks it's all mathematics. So if you don't, I often speak to the public and I try to get folks to understand that if you really want to dig deep into what I'm talking about, there's no way to get around the mathematics. Ah, Einstein. So even Einstein, one of our greatest physics heroes, was involved in the mathematics of describing gravity and light and what have you. And the equations I'm showing you here, which I'm not asking you to solve, but these are the equations that are the foundation of Einstein's theory of general relativity. General relativity predicts that gravity can move like a light wave, almost. So we're gonna look at some polarized gravitons now. So here's a polarized graviton coming from the rear of this image towards our face, and we're imagining we're in a circular tunnel and we're looking for the effect of the gravitons on the tunnel walls. And as you can see, it deforms them in this very elliptical shaped path that goes from the elliptic nature being oriented up and down or right and left. That's what a gravity wave would do coming out of a circular tunnel. But that's a linearly polarized gravity wave. What about a circularly polarized gravity wave? Well, wow, that's a much more interesting set of motions. Now, with LIGO, which is how we detect gravitons, we cannot yet detect polarized graviton waves. We can just detect the simple linear motion that I showed you. And if it can be polarized in the left-handed sense, it can be polarized in the right-handed sense. And now we're seeing such a wave coming from the rear of the tunnel. And you can notice that the twisting is actually in the opposite sense. So I told you that all the elementary particles that we are really good at seeing at places like CERN and the LHC, we've never seen the graviton, the particle that carries the gravitational force, and the particle that is predicted by Einstein's field equations. We know that quantum mechanics is an accurate description of nature. For example, the very devices you are using to hear and listen to me use quantum mechanics because the circuitry in modern information technology is all about quantum mechanics. So we have reasonably, on the one hand, if you step off of, if you step off a hill, you'll feel the influence of gravity. So that's pretty convincing. On the other hand, if you use computers and smartphones and what have you, you ought to be convinced about quantum mechanics too. So both of those are attributes of our universe. Well, shouldn't they work together? Well, it turns out the equations that Einstein gave us and comparing those equations to the standard model don't work together. In fact, they make no predictions at all. And this is a great mystery. Now, people like my colleague, Edward Witten, thinks about this in the context of string theory. And in 1995, Ed came up with this really interesting proposal that all of the strings that we had thought about as separate, that you can see indicated on the right side of this diagram by the words type 1, SO32 heterotic, E8 cross E8 heterotic, type 2A, type 2B, that all of those strings are in fact related to each other by something that he called M theory. So what is M theory? Well, to this day, we don't really know. We know parts of it. And part of it is a special limit called 11-dimensional supergravity. And that's what I want to talk about. And that's actually what I'm actively engaged in research right now, along with the objects that Professor Goins introduced us to, Dinkers. I'm going to see some of those shortly. So you can think about a world where there are 11 spatial directions. We only have 3 in ours, but remember, this is mathematics, so we can have as many as we want. So in such a world, there might be a particle that carries gravity. We're going to indicate it by this symbol. Now, the mathematical consistency says that if you want to write this thing down, you can't write it down by itself. Remember the standard model had lots of different parts? Well, those were built because of observation. For this thing, it's the mathematical consistency that demands the different parts. So here we see a thing called the gravitino. Here we see something called the three form. And mathematically, if you introduce the graviton, you have to introduce these things too, under the property of supersymmetry, that balance that we saw. It turns out that we can, remember that twisting sorts of motion that we saw? Well, mathematically, we know how to define those things. So in 11 dimensions, if you wanted to see the twisting motions of these things, what you would find is that the graviton actually has 44 twisting motions, not the 2 that we saw in our world. And that the gravitino, as this object is called, has 128. And finally, the three form here, A, has a set of twisting motions that when you add those motions to 44, it exactly balances to 128. Remember that left-right balance? Well, here we're seeing it in the numbers of twisting motions that are current and present. So, but you'll notice I have a not equal to sign there. That's because on the first line, I'm obeying classical mechanics, the laws of classical on-shell relativistic field theory. Whereas in the second line, I'm saying, well, suppose the world was really quantum mechanical, then the counting of these twisting motions changes and you get an imbalance. Now, this is a problem we first confronted a long time ago. And so people like me know about this problem, we've wondered about it. And up until recently, no one had actually solved this problem of saying, can you still restore this balance between the things that are like electrons and the things that are like photons in this imaginary world? Because you need this balance for the mathematical consistency. If you're classical, you can see that equal sign, but you also need the balance in a world where quantum mechanics is present. So I'm going to speed up a little bit. Here's a little bit of mathematical representation of these things called young tableaus. And then we do the counting. Well, let's go back through the history. In 73, people first thought about these things in 4 dimensions. They found the count without quantum mechanics works. With quantum mechanics, it didn't. In 77, a physicist named Brightloner figured out how to fix the problem. He said, in addition to the things that you want to describe, the math requires that you introduce more objects. And so I'm representing these more objects by dots here. I don't want to really talk about their details. And so the problem that for over 40 years had not been solved is how do you do what Brightloner did for M theory, which Ed tells us we need for the quantum consistency of the universe. That's a problem that I've been thinking about. And in order to solve it, I'm going to talk about how diversity comes in, because we're going to talk about how diversity actually works in science. Now, this is a picture of Rosalind Franklin, who most of you may have never heard of. However, she is the X-ray crystallographer who first accurately imaged DNA, which then Watson and Crick actually used as the basis of their paper, which is very famous. We call it the double helix these days. But this is the lady who first did it. In fact, they weren't very kind to her because they used her data without her knowing it. Now, her insight experimentally leads to the DNA, and here's the strand of DNA, which, by the way, we're very happy we know about, because this is how we are fighting back against the COVID pandemic, by knowing how to manipulate genetic material. In fact, there's something called messenger RNA, which is the prime component of both of the leading vaccines. So when I started thinking about this problem, at first I was thinking like my friends Ed and what have you, but you know, I'm obviously an African-American. I actually think a little bit different about mathematics. And so it occurred to me that there had been great progress in genetics by first thinking about things that are, in biology, we really want to think about living things like us and animals and what have you. But genetics tells us that we need to think about the parts that make them up. So I started thinking about the equations asking, do they have things like genes in them? And if so, can I use the same kind of approach biologists use for getting information about biological systems from their genes? I'm not the first physicist to think about this. In fact, a physicist named Max Delbruck started thinking this way in the 1930s. And in fact, I'm going to do the opposite. He was thinking about taking physics into biology and trying to use the methods of physics to understand biology. I'm going to take some biological hints and use them to do what I call sequencing equations. This is something I started in 2004 with another physicist by the name of Michael Fox. Our idea was the equations that Ed is talking about, you think about at this apex, they're very complicated, they're so incredibly numerous. And we thought if they're really part of some kind of grand theory, then maybe they have a kind of a shadow. And instead of thinking about this complicated theory, we can think about, well, maybe there's some kind of something that's like something like Rosalind Franklin's X-ray crystallography that allows you to study these equations by looking at different equations. And we found a way to do it. It turns out the way that we did this was by using ideas of Einstein about how special relativity tells us where we live. Now, Einstein was also another diverse character. We're going to come to that later, not too distant future. And so these are the kind of equations I study with my friends. In fact, you know, we've been doing this since the 1970s when I got my PhD at MIT. I was the first person at MIT to work on these kinds of equations on supersymmetry. But this sequencing thing that I told you about, Michael and I deduced that those equations that I showed you on the previous transparency have these mathematical genes, and you're looking at them. And by the way, I want to thank Edray for introducing you to these toys, because we're the people who actually discovered them in 2004, and we gave them a name, which I'll come to shortly. So these are the mathematical gene-like structures associated with the electron. Here's the equation that describe light in this balanced universe. These are their genetic signatures that we find by this technique that we developed. As you can see, it looks sort of similar, but you know, it also looks very simple. Ultimately, we discovered these things are the descendants de fond that Edray described in his talk, which came as a great shock to us and the group of mathematicians that we started working with. In 2010, there was a nice cover on the British Journal of Physics World talking about these objects, which we have given the name of adinkras to these mathematical gene-like objects. So what are they good for? Well, remember that problem I couldn't solve, but actually that nobody can solve? We're going to see shortly that using these ideas, we can solve them. So this idea of these genes opened up an incredible world of mathematics between physics, where you're talking electrons and photons and gravitons, and very complicated and deep mathematics about graph theory, as Edray mentioned, cubical cohomology, Coxeter groups, descendants de fond, Bélier pairs, Morse divisors, algebraic topology, geometry, and Bermuda-Hedra. So this idea of sequencing opened up an incredible world of mathematics for us. So in 2019, while I was here at Brown, I started thinking very deeply about using this sequencing to solve the problem that no one could solve. And we wrote a series of papers. I'm just showing you the covers. And here's what the sequencing looks like. You see, these symbols we call P, those are the things that talk about the physics. But the things that you see in the middle, that's the sequencing of these physical properties into things that are like genes. You'll notice that the combinations of what we call P1 are totally different from P2, P3, P4. And this is what tells us that electrons are different from photons, are different from all the other particles that we saw in the Standard Model. They have different mathematical genes in this construct. We have a couple of different ways of writing this. Sometimes we either write the way I showed you, sometimes we write it this way. But once you know about these mathematical genes, they begin to group themselves and you start to think, gee, this really does look like biology, because you have to take a collection of genes to form a biological structure. And we continued to study it until this year. And then we finally figured out that these genes are part of a larger mathematical structure called a Bermuda-Hedron. The mathematicians have been studying these sorts of things for over 100 years. This is the first time I'm aware that the properties of elementary particles are being related to these deep mathematical objects called Bermuda-Hedra. And so our particles, which we sort of talk about their types and colors here, you can see how they distribute themselves around the S4 Bermuda-Hedron. Now, this is kind of like what Murray Gell-Mann did back in the 60s when he first invented quarks. You know, protons and neutrons have quarks inside of them, and they form these nice, beautiful patterns because the quarks are inside them. And we begin to see this replay again in the context of thinking about biology. So we learned how to build these genomes. And so I'm just going to show you some pictures here. If people really want to have mathematical detailed conversations, I'm happy to do that, but that would slow us down. So we can build these things. They have graph theory, they're networks. Wow, wait a minute, networks. Where have we seen that before? Well, a lot of information technologies around about networks. Google actually works because it's about the studying of networks. And so networks are a powerful mathematical tool that is not normally brought to bear on thinking about things like gravitons, but we have found a way to do it. And so this problem that I was telling you about actually has 4.2 billion functions involved. And that's part of the reason why nobody could solve the problem. That's so many functions that you're going to just get lost in the nightmare as you try to solve them. But if you think about these things in terms of genes and asking the question where these different parts fit on the genomic structure, it turns out you can write computer programs to answer that question. Here's a picture of the genome that involves these 4.2 billion functions. These are its lowest levels. It's kind of triangular, diamond shape. And we've classified the different spinning structures that sit inside of M theory. And this is what our data looks like in terms of the computer codes that we use to study these objects. So they're kind of like crystals, but they're also kind of like genomes. And we have given computers rules for how to construct these things and study them. As you can see, the numbers start to get like ridiculous, but they do. But what's marvelous to us is that this is a way of thinking about the problem that you wouldn't get to unless you said, I'm going to think like a geneticist, not a physicist. And so I'm grateful that some of these graphics I've used are actually in a product that you can see owns the actual intellectual property rights. So I'm giving their due praise. These are my collaborators. I've been doing this work for over a decade with graduate students, postdoc, other physicists, mathematicians, and other folks, graphic artists, who really are the people who start me thinking visually about trying to solve this problem. Thank you. That's what I do right now as a research scientist. And let me tell you, it's like having Christmas every day.
Thank you, Professor Gates, for that wonderful presentation on your research. And I just think it's incredibly interesting how you yourself and Professor Goins did presentations also related to the shape of ellipses in a lot of ways when we were talking about the gravitons and those shapes. I just thought that was incredibly interesting, and what a coincidence. I don't know if this was planned behind the scenes, but it was definitely a very nice thread between both presentations.
Well, George, let me just tell you, I didn't know that Edray was going to talk about adinkras. I'd like to say adinkras are sort of my mathematical babies. And so I was very surprised when they came up in his presentation. But that's how often physics and math merge for us to increase our knowledge.
Absolutely. So yeah, now we come to the part of the portion of the Q&A. So we'd like to first thank the audience for fielding several set of questions, and I'll be helping to moderate. And our first question comes from Joe, not the Joe from MIT, my MIT counterpart, but Joe from the audience. So thank you, Joe, for the question. He would like to know, can you talk a little bit about the pipeline in terms of going from grade school all the way to PhD and then finding academic positions in relation to the fields of math and physics? And how does that process differ from, say, white males and other groups, people of color, other marginalized groups?
So I'm assuming he wants sort of an origin story answer as opposed to statistics, which is what my colleague gave. So I'll give my origin story first, and I'll let Edray give his. My origin story goes back to when I was 4 years old. My father was in the US Army for 27 years. And when I was 4 years old, I was living in St. John's, Newfoundland. I lived there for 3.5 years of my life as a young child. My mother took me to see a science fiction movie. It was the first movie I ever remember seeing. And what I understood about science then was it was a great doorway to adventure and fun. What else would a 4-year-old boy want to do? And so it started early with me because of that experience and exposure to science fiction movies. In my family, we have a very interesting relationship to mathematics. My grandfather could neither read nor write according to our family history, but he could do arithmetic. And so, that's kind of unusual. My dad never finished high school, but as a child, I remember watching him study for his general examination because he didn't get a college degree, rather a high school degree. And he studied trigonometry and some beginning of calculus. And I remember watching him as a kid, wondering what in the world were those mysterious figures. In fact, it struck me like, it's kind of like Harry Potter. You see all the strange symbols and they mean something. And that was the impact it had on me when I was about 7 or 8 years old. When I was 8 years old, I was having trouble learning to read. Not do arithmetic. That sort of felt very natural. So my father brought home some books on space travel that reinforced the fact that I loved space when I was 4 years old. I began to read very quickly. But then when I was 14, I learned about MIT. As far as I knew, it was a place where they made you study what I called the good stuff, the math, the physics. And so at 14, I knew that's where I wanted to go to college. And then finally, when I was 16, I had an amazing African-American physics teacher, a man by the name of Mr. Freeman Coney, who actually had a degree in physics. This is a rarity to this day in the United States. Most young people who take a high school physics course do not have a teacher with a physics degree. And that partly explains why we have such difficulty attracting young people into our discipline. And that is particularly true for underrepresented minorities, because we have a direct correlation in this country between race, wealth, and education. There are about 14,000 school districts in the United States. School districts pay for their education by property taxes. Therefore, if you're in a wealthy community, there's going to be much more money available for you to learn than it will be for kids who are not. So that's part of our problem as a nation, is everybody doesn't get a fair shot. And I understood that when I was in high school, because being in an all-black high school, we organized a chess team. We were the only black high school in Orlando. So we went to other high schools to play our opponents. We beat all of them, even though we came from the school that had very little resources. So I understood very early in my life that the odds were set against me. I'm the first person in my family to go to college. But I also understood that if you work really, really hard and are passionate about something like science, it is a doorway to escape the trap that has been set for you.
Yeah, it's amazing how similar backgrounds Jim and I have in this sense. I was also really, really interested in science growing up. And Jim joked that he kind of sometimes considers himself to be a failed mathematician. I consider myself to be a failed physicist. I loved physics growing up. Like, I could not get enough of physics. I just remember reading about various things in encyclopedias. I remember reading A Wrinkle in Time when I was in elementary school. Just that whole idea of tesseracts and moving around the universe, that just really ignited my imagination. By the time I was in high school, I remember reading this book called A Brief History of Time that Stephen Hawking wrote. Not really knowing much about the physics, about the mathematics. I remember hearing about these things called Lorentz transformations that I could not figure out, but just all of that got me fascinated in just the world around me. On the other hand, I hated mathematics. I did not like math. I did not like my math classes. I, at the time, thought that math was about doing competitions, that it was just about if you could do a problem really fast, really well, then that was math. I hated competitions. I did academic decathlon when I was in high school. I really didn't like it. And just the whole thing, just having to do these math competitions turned me away from mathematics altogether. So if you would have asked me if I would have been a math major or a mathematician when I was in high school, I would have said, definitely not. My whole thing was being a physicist. So I went up to Caltech, much in the same way for like the reasons why Jim said he went to MIT. I grew up in South Los Angeles. Caltech was always on the news because of earthquakes, as you might imagine. And so I knew at a very early age, I was probably also about 14 years old, I had to go to Caltech. I didn't even consider any other school at all in the country. Quick little story, my senior year in high school, I definitely knew I wanted to go to Caltech. Of course, my high school counselor was freaking out saying, you know, you shouldn't just put all your eggs in one basket, think about applying to other places. So I said, fine. I sent off a postcard to MIT to ask for an application. You know, these are pre-internet days, you can go on the web. So I sent off a postcard. I got back in the mail an application to apply to Caltech. It turned out that there was a guy who ran the diversity office at Caltech, Lee Brown. He made it a point of just sending applications to who we thought were the best Black students in the country. So I got an application from Caltech from Lee Brown. To this day, I never got an application from MIT. I have no idea what happened there. So just putting that out there for the people in the audience. That's the reason why I didn't even consider going to MIT. But because I got that application from Caltech, I was just over the moon. I just knew Caltech's where I had to go. So I went to Caltech and majored in physics and decided to take these math classes because I could learn about differential equations to help with the physics classes. And I was embarrassed. I am now embarrassed to say, I really, really enjoyed the math. And I spent a lot of time reading more number theory books, these books on the side. I never told my friends because, of course, I had to be a physicist. I was at the house that Richard Feynman built. But math is something that I really enjoyed. So I wanted to put all of this to say that my whole path was, I was definitely interested in science. Math was something that I started to like in college, but I shied away from it because I was really worried about this whole thing with competitions. So maybe I want to just step back a little bit to say that there's an organization that I'm involved with now called BEAM. It's Bridge to Enter Advanced Mathematics. They actually have programs that they run in New York City and now programs that they run out here in Los Angeles. But this program is actually meant to take kids, mostly Black and brown kids that live in like New York and Los Angeles, and try to expose them to mathematics, but not in the sense of competitions. Really, it's supposed to be the opposite. It's supposed to be either a summer program or Saturday program to really tell these kids, math is actually something really fun. Even if you hate competitions, math is still really fun. And this is something that I think is extremely important these days, to really show kids that if you're going to do mathematics, it isn't just about the very narrow idea of you have to do competitions, do them really well, go off to the top schools, then you'll do math. I mean, math can be extremely fun if you just do it just for the sake of kind of the knowledge that's there.
That's fantastic. Thank you both for sharing. And Professor Goins, when you mentioned math competitions, I just remembered my time with the AMC, Amy, math counts, and absolutely. I completely empathize with that fear of, I remember like when you were talking about all those different shapes and the torus, I just remembered sitting in linear algebra and just, oh man, do I have to be tested on how fast I can calculate this in my head? I mean, it's a 9-nested eigenfunction. There's no, I couldn't do it in my head, but no, thank you so much for sharing. Our next question is from Aman Desai. I do apologize if I did not pronounce your name correctly. Please feel free to correct me in the chat window. But Aman would like to know, as in relation to liberal arts colleges and for specifically in the roles of TAs, what role do TAs have to play in making math and physics more equitable and welcoming to students from underrepresented backgrounds?
I can start that off because this is something that actually that I love about Pomona College. In fact, I just moved here to Pomona College about 2 years ago, specifically for this reason, actually. Here at Pomona, we have what are called mentor sessions. Now, in most schools, you have the idea of like a teaching assistant or like a TA recitation, where basically if you're a student, you're working on homework and say outside of lecture, you might go to a recitation where you sit in a room and essentially the grad student goes to the chalkboard and they say, let's discuss problem number 1. And they basically write out the solution up there on the board and you're sitting there as a student, you feverishly copy down the notes and then you're done. That's not the way it works at a place like Pomona. And I wanna say why in a sense of how this helps out women and minorities. Here we have more or less peer mentoring when it comes to working on problems. Students get into a room and they're supposed to kind of work collaboratively, like, around these movable desks. And the mentor, this is the student that acts as the TA, more or less facilitates the discussion. So the mentor is not supposed to go to the chalkboard, not explain things, but this person's supposed to help make sure the students are working together effectively in groups. They're asking each other how to work on things. This is something that's extremely popular here at Pomona. One of the things that's really depressing here about the COVID lockdown is in the math building at Pomona, it is the hot hangout spot on the weekends and the evenings, what have you, because you have students hanging out in the classroom, working on assignments together, cracking jokes, playing music. I mean, all of this stuff. It's just like this incredibly fun atmosphere of people working trying to understand these problems. Now, what I think works well for minorities in this sense is a lot of times you can feel left out of study groups. I mean, I can tell you a quick story. When I was in grad school in my very first year, we would have study groups to kind of work on homework problems, but I actually didn't know about any of the study groups. People were working on homework problems, preparing for their qualifying exams in the first year, and I had absolutely no idea until maybe 4 months into my first year of graduate school. Absolutely no clue. I think that this happens a lot, unfortunately, with minorities, that they're left out of study groups, they're left out of discussions, and because they don't really feel that sense of belonging in the math community, they just drop out. They just don't go to math classes. They don't go to the recitation sessions. The idea here of the mentor sessions is to say, we are all going to work together. So you literally come to the mentor session, you just walk in the room, and this mentor, this quote unquote TA, will say, I'm going to put you together with this group so that you can all work together. And it works out remarkably, remarkably well. I really think that this model is something that other schools can use and use it quite effectively.
George, can I chime in on that one? Because the question is actually very interesting, and I thank the questioner for asking what can TAs do. So as some of you probably know, I was an advisor to President Obama for 7 years, from 2008 to 2009 to 2016, 7 years. And one of the things that we did during that period was to ask questions, not just about minority students, but the question was, how can this country be more effective at teaching STEM subjects to all of its students, including minority students? And one of the things that there is documented research literature to support is that having a professor or a teacher stand at the front of the room where their back might be turned to the students entirely, especially at the university level. We've all been there, folks, let's admit it. But the actual research literature in learning and education has shown that techniques called active learning, which is what Edray was describing, that these techniques work to increase everyone's efficiency as learners, but it has an especially positive impact on women and underrepresented minorities. The fact that we as a nation have not gotten this message, that universities have not changed over, it's on us. And so one of the things that if you're a young person who is a TA, and I know you have to have your recitation done every week, and your students probably want to know only how to do the homework, but if you can get them, to understand that they are capable of teaching themselves in what's called peer-to-peer learning, that's a much more powerful tool than you spending just an hour working on the problems. Spend a little time letting them struggle, letting them get their sea legs, letting them understand the power of their own intellectual ability, because that's the real secret. But as Edray says, lots and lots of universities don't seem to get this message to this very day. And this is research literature that's been out there for almost 20 years.
Can I follow up, Jim? And I'm going to ask you about this because you've been very involved with not only educational structure there in Maryland, but also this thing called TIPSY, Transforming Post-Secondary Education in Mathematics. I 100% agree with you that the idea of active learning, having a flipped classroom, something where the professors are trying to be a little bit more engaging, or at least I should say, having the students to be a little bit more engaged with the learning process is very important. Also, a lot of us are used to the Research One environment where you do passive lecturing. You get up to the front of the room, you turn your back, you lecture at the board. That's just what we're trained with. I want to ask you, how do we get faculty to do more active learning?
I'm going to say something terrible, so everyone should be warned. Someone once asked a question, how does progress occur in physics? And the answer is one funeral at a time. That's a terrible answer. And we would hope that it's not true. But the point is, I and the 30 some odd, this is I'm in my 50th consecutive year of teaching students right now. And so it is, my hopes are for the younger generation, because I know that even students that I think of as just bursting with potential to do physics at its highest level, even among that group, I hear people, how can I be a better teacher? And this is something I think is actually comes from the way young people have interacted with social media before they get to us. They are much more connected to each other. So my hope is that they will begin to bring some of that experience as digital natives into their experience and the responsibilities as instructors in STEM disciplines.
Well, I can add to that. What I have learned in this day of teaching online with COVID-19 is, by necessity, I've had to flip my classroom. You know, I cannot sit in front of the screen and lecture for 50 minutes because, I mean, well, students can turn their cameras off, probably pick up their phones, start doing some other crazy things. So I have really figured out that it's a good thing to have breakout rooms to kind of break things up, flip things around, let them chat a little bit more. I feel like my lecturing has actually gotten better in the years that we've had to be online than it has in all the years that I've taught, really because this whole thing of using the technology, using what the students enjoy, I think has worked out a lot better.
You're not the only person, Edray. Actually, there's an article in the August issue of the American Association of Physics Teachers that spotlights my summer. As you know, I run a summer program. That's how I can say I've been teaching 50 consecutive years, because I run a program where undergraduates become part of my research group. Sometimes even high school students become part of my research group, and I publish with them. In fact, we just posted about 2 weeks ago 2 papers with 5 of my undergraduates from this past summer. And so, but this was all done by using Zoom. And I, like you, learned that Zoom forces you to think in a different way about how to be an effective teacher. And one of the things that Zoom really, and you put your key on the thing I think is most interesting about this technology, it's the breakout rooms. Because, and Zoom is not perfect in this regard. GatherTown is actually more my favorite. I don't know how many of you have actually used GatherTown, but there are other apps that they effectively create. It's like being in a real world classroom with students at tables, and you can go over to their table and talk to them and see what they're talking about. And to me, that ability to actually sort of guide students' thinking, be there when they get stuck, not to answer the question, but to offer a hint for how they can answer the question. I can do this much more efficiently online than I can in the real world. So I'm a big fan of what I've learned over the last year about teaching online. But we've got to do it. It can't be us giving a television program. We can't just stand there and talk.
Definitely.
Absolutely. Thank you both for I mean, that breadth of not just answers, but advice and also observations. And I think going along those lines, I think there's a lot of questions in the audience from Celia, Valerie, and Leah, and others around education itself. You know, well, how can we have students in general at all different levels from primary school through university, get them to be more interested in maths, physics, the sciences, and STEM in general? And then on top of that question, how do we encourage more people of color to be interested in STEM? And is that is that a way of like pedagogy issue? Is that, I mean, we talked about accessibility issues and resources. What are your thoughts there?
May I, since Edray, I think you began the last answer, can I start this round? Thank you. This is something, Georgia, I have thought about a lot, and I've actually written about it. But, to me, the key thing has to do with the culture in which we're all embedded. Namely, many people responsible for teaching, especially technical fields, when confronted with a class that involves minority students, will have what educators call a deficit mindset, that they model the student as having something internally wrong and they're trying to fix it. This is in opposition to what educators call a growth mindset, where the point of the instructor is to figure out where the strengths in the people in front of them lie and to meet them where those strengths are to increase their ability and mastery. So and this whole thing about culture, is to me the biggest barrier that I've seen. And I've seen it play out on all kinds of scales. I mean, it impacts my research, quite frankly, and what I'm able to do, all the way down to a story I told a few years ago in science about this class I was teaching that had a couple of African-American students in it, and they were working in small groups, because I believe in active learning. And I watched the interactions between this single African-American student and the students the other students in the group. At the beginning, they had that deficit model of the African-American student. But through some interactions, it became clear to everyone at that particular table that the African-American student actually learned faster than anyone else. And if you accepted that, your whole group could learn faster and do better. So it's this whole thing about what we carry as apps inside of our head that is the largest problem. It's not the lack of resources in many ways, although that is a barrier. But this whole mindset that there's a class of people who can't do, that are just intrinsically not capable of doing, this is a major problem for our society.
Yeah, I 100% agree. I think one thing along these lines that I think about in mathematics is this idea of, I'll say gatekeepers, or you can even say gateway courses. You know, there's a lot of discussion these days about how do you get kids, I should even say college students, to become math majors, to eventually maybe go off, graduate, to get a great PhD. And you have to worry about the kinds of classes that they have to take as they're starting out. I can tell you that at Pomona, one of the things that we try to be very careful about is, say, for our calculus classes. We realize that for a lot of students, the first time they see math in college will probably be calculus. Now, if you have a calculus class where you scare the students away because of things like maybe very competitive classes, the students not really feeling like that they're part of the community, then of course they're not going to stay in the major, they're going to move away. Like calculus really is in some ways a gateway course. It's going to be that first course that a lot of students are going to see. I can tell you, I myself am very worried about teaching calculus because I feel maybe I'm not the friendliest person, and I really want to make sure that we have enough friendly people teaching those classes to really encourage more and more students into the major. But it is a big question, and it's very difficult. I think that we are losing a lot of minority students because of exactly the things that Jim is saying here. You know, like deficit mindsets is a real problem amongst a lot of professors. And I can even tell you it's something I myself really have to think about quite a bit, you know, making sure when I see a minority student, when I see a woman, I just don't assume they're in my office because they're doing really poorly and that they need help. Like I really have to remind myself at a place like Pomona, they're high achievers. They're doing really, really well. They probably know this stuff at least as well as any other student here in the class. So I do need to meet them where they are, see why they're in my office while they're talking, and then to see if I can really encourage them to do better. You know, I don't know how many professors do this, but I think that for a lot that don't, this is really driving a lot of our minority students and our women, unfortunately, away from the profession.
And if I can just pivot off of your comment earlier, Edray asked me to comment about TIPSY, Transforming Post-Secondary Education in Mathematics. This is a group of educators and esteemed mathematicians. I mean, the former president of the American Mathematical Society is part of the leadership of this group, and faculty who established interdisciplinary math research institutes at the UCLA are part of the leadership of this organization. And they are kind enough to let a physicist come in among them. So I'm also on the board of directors of this organization. In fact, this organization, in my mind, is one of the most wonderful events in my life, because in one of our reports to President Obama, we called for the creation of something like this. And it turned out that the mathematicians were already thinking about it. And our report to President Obama on post-secondary education acted as a spur. And so TIPSY has been out there. And one of the things that TIPSY is working on is to move other courses into the gateway role, as opposed to just the traditional use of calculus. And so I watch my mathematician friends with great admiration and appreciation as they wrestle with moving this traditional mindset from their colleagues and themselves.
Yeah, it's a remarkable project. It's really just amazing, like how much it's really transforming the field. And I mean, we're having discussions about things in math culture, in the gateway culture, that I don't think that we've ever really had before. And I should add that this is not just in math. We're actually starting to have discussions about statistics, about data science. You know, how do you get students interested in careers in data science? And it's the same question: what classes should they take? What should be the mindset in these classes? So, I mean, these are a lot of very deep questions we're having in the math culture.
Absolutely. I think just as a person of color as well, and who had taken, I mean, I tried to pursue a degree in applied math, but it didn't last very long. But everything that you both are saying, I definitely have experienced myself, and to see two leaders in this field address these issues and, you know, be a part of these organizations, it's incredibly inspirational. So firstly, thank you. And yes, we still have a lot of work to do. I guess going more on the math side, someone asked, why is math so good at describing physics? You know, I think math and physics, or calculus, I should say, and physics go hand in hand in so many beautiful ways. Why is it just innately such a good explainer? Or, you know, are there other types of explanations we can look at? And I think Professor Gates, when you showed that that cross synergy of looking at physics through the lens of biology is very interesting, and wanted to ask if you both could comment on that.
Jim, you want to take that one first?
Thank you, Edray. First of all, this is a question I have been asked often and deeply many times in my life. There is a video at YouTube. It was sponsored by the New York Academy of Sciences. I think it's called The Mystery of Mathematics. And this question came up in a certain variation. And my response was the following, that, so, you know, people often ask, is the mathematics in nature, right? Is it somehow in nature and we get it from nature? And my response is, I don't think so. What I think is going on is that mathematics is the only human language that we have discovered to date that it has the capacity to accurately describe natural processes. And so to me, it's not out there. It's actually part of in here. I mean, mathematics, from as I've experienced it, actually comes from our subconscious. And that means it's definitely part of us as far as I can tell.
Yeah, I agree with that. You know, when I was a double major with math and physics, I often debated whether math is a science. And I can tell you now, I consider math to be more of an art. You know, a lot of mathematicians do debate this whole thing of, is math invented? Is math part of nature? I don't know where I come down on the fence. I just know that for a lot of math people, we study it because it's inherently beautiful. Like, I mean, we literally like the symbol. Sometimes we write integral signs up on a chalkboard just because it just physically looks nice to look at. You know, there's times when I have been in a math class and I'll watch someone just write out the whole lecture at the chalkboard, but just the handwriting is so beautiful, I'll just sit back, just enjoy it. I may not understand any of it, but you know, but it just looks beautiful to be there. So I know that a lot of math people, they like the elegance, they like the symmetry of it all. I think that's what convinced me to go from being a physicist to being a mathematician. What I liked about physics, what I still like about physics, is that I do think math does a really good job of at least approximating what we see in reality. It maybe doesn't hit it 100% on the nose, but it does remarkably good approximations in many cases. I think eventually other areas such as chemistry, biology, they will get to this point where the math would do a really, really good job of approximating everything that we see. But I know that math folks, as weird as this sounds, a lot of us don't care so much about Are there applications to physics? Does it describe the world around us? We just think that it just looks beautiful. And we just do it because of the beauty that we see in it.
So the other thing I would add, the final point I would add to this is some of us actually dream about mathematics, which may seem very weird, but it has real world impact on the mathematics that we do. So, I mean, that's why I said mathematics, as I have experienced, is an extraordinarily deep part of my subconscious.
That's wonderful. I mean, that's beautiful. Talking about math as art, and I think like it's kind of similar like when you play chess. You know, I think everyone thinks it's very mathematical, but once you get to look at all these beautiful games by like Kasparov or Magnus, you realize, whoa, they're looking at the game like the way you're describing about math and physics. It's not, and that idea of the subconscious being into play, it's absolutely fascinating. And in relation to math and physics in your presentations, I want to ask you both, what did you think about each other's presentations? And what were your favorite parts? And we'd love to hear your thoughts there.
So I want to start because I want to embarrass Jim here for a moment. I forget if Jim actually said this, at least while we were on the air. We've known each other for a very, very long time. You know, I first met him back when I really, really wanted to be a physicist. I just wanted to meet within the community of Black physicists. I remember going to the annual conferences of the National Society of the National Conference of Black Physics Students, and just feeling very, very welcome in that community. Jim and I have always talked about possibly working on a project together, but it seemed like we could never really find the right project to work on. You know, I have been trained classically in number theory. I had an advisor that worked in representation theory. At one point we thought, well, representation theory is used in physics. There might be a way we can get all of this to work, but we could never really find anything to work out. One day, Jim was visiting Purdue University. He was actually giving a big distinguished lecture there. And we just happened to be in my office. There was some downtime. So I wanted to know about these things called adinkras that he had been telling me about for years and years. And I think at one point in the conversation, he just kind of offhandedly mentioned, yeah, and I heard from one of my collaborators that they're related to these things called descendant funds. That perked up my ears because I had been working on descends for several years at that point, and I had no idea that they were related to physics. So ever since then, I've actually been really obsessed with the adinkras. You know, what I like about Jim's presentation, really what I like about Jim in general, is he likes to see connections with all of these things. And you know, they're like unseemingly related connections. Like to me, having these graphs that you see from West Africa should have nothing to do with string theory, and they in turn should have nothing to do with elliptic curves or even differential geometry, but they do. And it's just amazing to me, not only that there are all of these connections, but also it's amazing to me that someone like Jim can really see what all of these different connections are. So, I mean, I've seen Jim give many talks over the years, but I can say I always enjoy watching him give a talk because I learned something new about a connection I had no idea before. Like I can tell you, to me, it comes out of left field that you would say the genome would come into play with the dingus. I would have never seen that coming. But I have to say, like, this is one of the things that I've always enjoyed about Jim, not only as a person, but as a researcher, that he sees all of these different connections and how they're all related.
So George, let me, you didn't mention Jose Raul Capablanca among the chess players. Some of us have misspent teenage years playing chess. So
no, he is quite a wonderful player, yes.
Okay, there you go. But back to the subject, you know, the way I think about it is, if you are so fortunate to have a mind that sees the intrinsic beauty in mathematics, that is such a gift. And it is also such a source of joy for those of us who spend, you know, our entire lives thinking about mathematics. Now, I do it very differently from Edray, and as he said, I'm really thinking about physics problems, but it's the purity of the statement of the problem that I get to by using mathematics. And that's how I see these connections that no one else sees. It's the purity, the crystalline purity of the logic that mathematics forces on the human mind that to me is the secret of its power.
Wow, just wow. Thank you. So we are at the last 5-minute mark, so we'll try to get a few more questions in. One question comes from Valerie, and I think this goes back to the mathematics competition part that Professor Goins, you were sharing with your story with mathematics and physics. What should or could the testing industry do to improve this pipeline? For instance, is the Putnam Math competition going to affect this kind of social change? And in terms of relations to DEI, what can these competitions do better to encourage and promote and develop energy and supporting people who may be marginalized by these competitions?
I'm going to try to answer that quickly, and I'm actually going to turn that on its head in a minute. I'm going to ask Jim a question also along these lines. I think there is a place for these competitions for people who really like the competitions. Like, yes, there are a lot of mathematicians that like the Putnam exam. They like these kind of problems and questions. So I'm not saying that they should be completely done away with. I do think that there's a place in math culture for it. Where I worry more is about using this idea of competitions and exams as a gatekeeper for those getting advanced degrees. Things like worrying about the graduate record examination, the GRE, as a marker for when someone should get into graduate school. So I wanted to ask this to Jim. My understanding is that the American Physical Society, I think, did a study some years ago where they looked at whether GRE scores were a good indicator of how well students perform in graduate school. And my understanding is that it is not a good indicator at all. So, and I know this is something that the math community is starting to look at.
Yeah, I mean, it wasn't done by, I don't think it was directly done by APS, but in fact, there have been a number of studies, including studies that go all the way back to Educational Testing Service, where the question is, how good is SAT at making a prediction of a student's performance in the first 2 years? And the sort of secret that no one ever seems to get to, so they're not really good indicators. And there's actually scientific data that you can look at to show that. Now, that's not known by the general public, for example. The public thinks that, oh, if you get a, 800 on your SAT, you must be a genius. Well, that's not really what the evidence does not support that belief. Let me just talk about something slightly different that I think is equally important that you commented about, Edray. And you were talking about tests. I think the secret for people to get to love mathematics more is computers. You see, computers, at least to my mind, are to mathematics what musical instruments are to scores. Namely, scores, you play them, right? They're a beautiful symbolic language, but you really feel their power when you play them on an instrument. The thing that to me is so remarkable about computing technology, and we're just starting to see it now, is that when you learn to code very well, it changes your relationship to mathematics. And then one of the things that's really interesting, and even in places you wouldn't expect it, mathematics, I've often predicted that at some far distant point in the future, we're going to see mathematical genius emerge among humanity who have no knowledge at all of the symbolic way we represent mathematics. They will do it through the playing of the instrument, which we call the computer. I think that's where we're going as a species, that mathematics will become more available to people as more people get into computing things.
That's an absolutely wonderful way of looking at the future of math, because I think, for example, with Markov chain models, I know when Mark Zuckerberg was at Harvard, he did research on social networks using graph theory and Markov chain models. And he did it through his computer. He programmed a model, so to speak. Yeah, that's very exciting. And well, we've hit the 2 o'clock or the 2 o'clock mark for Pacific Standard Time, the 5 o'clock mark for our friends at MIT. And this concludes the recorded portion of our webinar, but please feel free to stay on as we have another list of questions to be fielded. Feel free to hang out and chat. And on behalf of MIT and the Caltech Alumni Association, for those of you that have to leave at this time, we just want to thank you for tuning in for this Forum for Equity broadcast. Thank you to Professor Edray Goins and Jim Gates for volunteering their time to lead the discussion, and a humongous thank you for your contributions to the maths and sciences, and also for people of color. And it's because of your work that people who may not have the opportunity to study these fields do. So thank you for your work. And of course, as a community, we will continue to do more. If you have any ideas for topics or speakers in the series or other feedback, please reach out to alumnilearn@mit.edu or contact the Caltech Alumni Association info@alumni.caltech.edu. We'll be sure to forward all these questions asked in the Q&A to our speakers today as well. And we'll keep the chat window open for discussions for about 15 more minutes. And we'd just like to remind everyone that this broadcast will be available on the MIT Alumni Association YouTube channel within a week of today. Thank you so much for joining us with the MIT Forum for Equity, the MIT Alumni Association, and the Caltech Alumni Association.
Thanks for joining us. And for more information on how to connect with the MIT Alumni Association, please visit our website.